Hello everyone. Today we're going to discuss systems of three linear equations in three unknowns. Previously we have seen linear equations in two unknowns, such as this general form ax plus by equals c. And when we graph the solutions of such an equation in the Cartesian coordinate system, we would end up with a straight line. And of course, even though there are infinitely many points on that line, all we need are 2 points to be able to accurately depict the line, because we've previously discussed the fact that two unique points in a plane determine a line. By unique here we mean distinct. So they have to be different points. We can't use the same point. One point would not be adequate. In the same way, if we add a new variable, we're basically going to have not just the familiar x and y axis, we're going to get a new axis perpendicular to both of those, which we call the z-axis. And then we get the three-dimensional Cartesian coordinate system rather than the two-dimensional plane that we're used to. And whereas the graph of these equations in just two variables gives us a straight line, the graphs of these kinds of equations with three variables, ax plus by plus cz equals d, with x, y, and z being the variables, and a, b, c, and d just being real constants, then what we end up with is a plane, not just a straight line, but an entire plane. And whereas here we only needed 2 points to determine a given line, with a plane we need 3 points, 3 distinct points to determine the plane. What that means is if you have 3 distinct points in space and you graph a plane that goes through them, then you've graphed the only plane that will go through them. Any other plane that will go through them will coincide with this one or overlap with it, just as that's what we meant with lines. So you can have many different equations that when you graph produce this line, but they will be just constant multiples of each other. There's only one unique line that will go through those 2 points, and the same way goes with planes as well. Now, if you take more than one such equation, in this instance, for instance, in this section, we're going to be dealing with 3 such equations. What you're going to end up seeing is one of these 8 scenarios. When you look at any 2 planes or 3 planes in the space, they can interact in one of these 8 ways. Like, for example, in this first case, you can see the 3 planes coincide. In this one, you can see 2 of them coincide and the other one is intersecting it. Here, such a system describing this graph would have infinitely many points, namely the points on that intersecting line. Here's another scenario where you have 2 planes that are coinciding and another plane that's parallel to it. If you were trying to find a solution for this system, there would be no point that would be simultaneously on all 3 of those planes. Therefore, this system would actually have no solution. And the same goes with this system, or this one, or this one. So the only planes that would actually have solutions would be this one, which would have obviously infinitely many solutions, same as this one. Number 6 would have only one solution because the 3 intersect at one point. And this again down here, number 7, would have infinitely many solutions as well, all the points on that intersection line. And this one obviously would have no solution either. Now, in most applications, the type that we're going to encounter are the type that have only one solution. So in this section, we're going to be focusing on those kinds of systems, type 6, which are going to have just one solution. Now, if you want to solve a system with 3 equations and 3 unknowns, such as this one, you can see that even though solving a system of 2 equations in 2 unknowns was not the most efficient approach when it came to even 2 equations in 2 unknowns, yet it wasn't all that bad. But you can see if you were to try to graph each of these planes every time you want to solve one of these and then try to find that point of intersection, that would be quite a feat. So we definitely don't want to approach these kinds of problems graphically, although I have provided a graph here for you to get an appreciation for what you're actually looking for. You are actually looking for that point of intersection when you solve such a system, because you're going to find not an ordered pair xy, but you're going to find an ordered triple of this form, x, y, z. And the way we're going to approach these is going to be the following. We're going to try to take this system of 3 equations and in 3 unknowns, and we're going to somehow cleverly try to reduce it down to just 2 equations in 2 unknowns. The way we're going to do that is we're going to scope the 3 equations and see if there is any one variable that is easy to eliminate twice. So we can take any pair of these 3 equations and eliminate a variable, and we're going to do that to 2 such pairs. Now we notice that it's possible to pick any of the letters, the variables. However, it looks like the easiest one to deal with will be x, because it will be very easy to eliminate x from, for example, from equations 1 and 2. It will also be very easy to eliminate it from equations 2 and 3. So that's exactly what we're going to do. We're going to start with equations. Let me go ahead and call these equations 1, 2, and 3. And we're going to work on that. So the first thing we'll do is we'll go ahead and eliminate x from equations 1 and 2. That's going to require us to multiply the second equation by -2, and what we end up with is -2x minus 8y plus 4z is equal to -18. We're going to leave the first equation alone, so we get 2x minus 5y plus 3z equals -1. So we go ahead and add those 2 equations now. Notice that these will cancel out, and we end up with -13y plus 7z is equal to -19. Now that's a new equation that we have come up with, so let's go ahead and give it a name. We'll call it equation 4. So remember, we're gonna eliminate the variable x twice, and you'll see in a minute why we're going to do that. So let's go ahead and eliminate x from 2 and 3. So why don't I multiply that equation, which we called 2, by -1 to get -x. We're multiplying this equation by -1 on both sides. So we get -x minus 4y plus 2z equals -9. Be very careful with the signs. This process, you will see, is simple, but there are lots of places where you could make little mistakes. So you have to be in real samurai mode to do these. All right, so for equation 3, we're just going to bring it over. This is what equation 3 was. So x minus 2y minus 4z equals negative 5. We're just rewriting that. We're not multiplying by anything. All right. So now if we add these two equations, again, those two will cancel out. We get negative 6y minus 2z equals negative 14. Now, the nice thing here is that we now have two equations in y and z. Let's go ahead and call this one equation 5. So now what we will do is we'll take equation 4 and equation 5 and we put one under the other. So we have negative 13y plus 7z equals negative 19, and we have negative 6y minus 2z equals negative 14. Now, at this point, we're going to solve this simple system that we know how to solve. It's just a system of two linear equations in two unknowns. We covered that in the previous section. Now I could just eliminate z by multiplying the top equation by 2 and the bottom equation by 7, or I noticed that I have a constant GCF of negative 2 which I can get rid of. Let me do that first because that's going to make my life easier. So we're going to divide basically each of these terms here by negative 2, and we end up with 3y plus z equals 7. Now this one we can just leave as is. We have negative 13y plus 7z equals negative 19. So now in order to eliminate z, all we have to do is multiply the bottom equation by negative 7. So we'll leave the first equation alone. And we multiply the bottom equation by negative 7. Don't forget that because of distribution, each of those three terms needs to be multiplied by 7. So we get negative 21 y minus 7z equals negative 49. Now we're going to add those two equations and we're going to get negative 34y is equal to negative 68. Then we go ahead and divide both sides of that equation by negative 34, and we end up with y equals 2. That's beautiful because now I can take that value of y equals 2 and I can go into basically any of these four equations and get the value of z. Of course, I'll pick that one because that's the easiest one to work with since z has a coefficient of 1. So we use y equals 2 in this equation. And we get 3 times 2 plus z equals 7 So we get 6 plus z equals 7, and we end up with z equals 7 minus 6, or z equals 1. Okay, so we're almost there. Remember, we need all three variable values for this solution, so x, y, and z. So we're still missing x, but that's easy because we can just take this y equals 2 and z equals 1 and go into one of our three original equations and solve to get z. And it looks like the last one, number 3, is the simplest place to go. So we're gonna use z equals 1 and y equals 2 in 3 to get x. So when I plug in into equation 3, I get x minus 2 times y, which if you recall is 2, minus 4 times z, which as you can see is 1, equals -5. So we get x minus 4 minus 4 equals -5. So x minus 8 equals -5. So x equals -5 plus 8. So we get x equals 3. So for the solution, we have come up with the order triple. And remember, that's only one solution. That's why the graph is so helpful, because you can see there's just one point in space that's going to satisfy all three of those equations represented by these planes. And the order triple, you always start with x, then you put y, and finally z. So you can see that point of intersection that our graphic program had indicated is in fact the one that we found, 3, 2, 1. Now, whenever time allows, it would be a very good idea for you to go ahead and check, and of course that would not be difficult. You just go ahead and substitute 3 for x, 2 for y, and 1 for z into all three of those equations. Make sure they become true. And so for the first one, we have 2 times 3 minus 5 times 2 plus 3 times 1. We want to know if that's equal to -1. So here we have 6 minus 10, which is -4 plus 3, and that is 6 minus 10, -4 plus 3, which is -1. So we get -1 equals -1. That one checks out. We can check equation 2 right here. So we're going to substitute once again 3 for x, 2 for y, and 1 for z. So we get 3 plus 4 times 2 minus 2 times 1. And we're checking to see if that's equal to 9. And of course on the left we have 3 plus 8, which is 11, minus 2, which is in fact 9. So we get 9 equals 9. This one checks out too. And the last one, we're going to do the same substitution. So we get 3 minus 2 times 2 minus 4 times 1, and we're trying to verify that that's equal to -5. On the left side, of course, we have 3 minus 4, which is -1, minus 4, which is -5. So once again, we get -5 equals -5, and that checks out. So we can be certain about the solution that we found. All right, so that's basically how you do these. As you can see, the process is not difficult. It's simple, but Also, as you can see, there are many places where simple errors can be made. So be very careful when you do these, and you shouldn't have any problems. So make sure that you absorb this. A great thing to do would be to pause the video, write the problem down, see if you can go through it yourself. And the general process I'll repeat. Basically, you have three equations, and what you do is you take two pairs of those three equations and you eliminate the same variable. So you want to eliminate one variable twice. And the reason you do that is because of what you noticed happened. Because when you do that, you end up with two new equations in only two unknowns. Which unknowns? The ones you didn't eliminate. Remember, we didn't eliminate y and z, we eliminated x. So that's why the two equations that get left behind are going to be in y and z. Then you just take those two new equations that get generated, you form yourself a new system, and now that's a very simple system in just two variables, and you can solve those using techniques of the past. Here we used the elimination technique, and that's all there is to it. And of course, if time allows, make sure you check. So again, make sure you can do this on your own before you proceed while I erase the board. Okay, let's take a look at another problem. This time, when we look at the coefficients of the variables in each of these three equations, we notice that z is going to be the easiest variable to eliminate. There are different options, but for example, you can eliminate z from equations 1 and 2, and also from equations 2 and 3. So that's what we will do. If you think you can handle this on your own, and I think you probably can, you should pause the video and try it on your own before you come back to join me. Okay, welcome back. So this time, when we try to solve this system of three linear equations in three unknowns, we can see the system depicted here. We're looking for that point of intersection. And when we look at the three equations and the variables and their coefficients in those three equations, we can see that the easiest variable to eliminate is going to be z. That doesn't mean if you have a particular preference for x or y, you can't eliminate those. You can, but as far as efficiency is concerned, z is definitely the easiest variable to work with. So that's what we'll do. And in order to eliminate z from the first, we can, for example, eliminate z from the first two and then from the second and the third ones. And in order to eliminate z from the first two, we're just going to multiply the top equation, which let me go ahead and call them equations 1, 2, and 3 again. We'll multiply equation 1 by -2, and we get -6x minus 4y minus 2z equals -16. We bring equation 2 over without changing it, so we have 2x minus 3y plus 2z equals -16. So we go ahead and add those two equations now to get -4x minus 7y equals -32. And that's a new equation that we have, so we will go ahead and call it equation 4. Now we're gonna do the same thing in the sense that we will eliminate z again, but this time from equations 2 and 3. So that seems to be quite simple. We just need to multiply equation 3 by 2, and that should get the job done. So we'll bring equation 2 as it is, 2x minus 3y plus 2z equals negative 16. As always, I highly recommend that if you do know what's going on from this point forward, you should pause the video and try to finish this on your own before you come back and join me. For the third equation, we will multiply that by a 2. So we're going to multiply equation 3 by 2, and we end up with 2x plus 8y minus 2z equals 40. So we go ahead and add the two equations again, and we end up with 4x plus 5y equals 24. All right, so that's also a new equation. We'll call it 5. And if you remember, we're now going to take equations 4 and 5, and we're going to form a new system. So equation 4 is negative 4x minus 7y equals negative 32. And equation 5 is 4x plus 5y equals 24. Now we go ahead and combine those two equations to get the x's canceling out, and we get negative 2y equals negative 8. Notice we had a lot less to do than the previous problem, because this just happened so that the two equations were already ready to be solved by eliminating x. That was just a fortunate thing that happened. It doesn't always happen, as you saw in the previous example, but when it comes our way, we'll take it. So now we go ahead and divide both sides by negative 2. We get y equals 4. So now we can take that 4 for y and plug it into either of these two equations. I'll just go with the second one. So we have 4x plus 5 times 4 equals 24. So we get 4x plus 20 equals 24. So 4x equals 24 minus 20. 4x equals 4. So x equals 1. So now we have x and we have y. We still need to find z. We can go to any of those three equations to get z. And of course, we'll go into that last one because that seems to be the easiest one, or even the first one. That's a positive z. That might even be better. Let's go to the first equation. Either one. You can go to any of those three. So we're going to use x equals 1 and y equals 4 in equation 1 to get z. So we have 3 times 1 plus 2 times 4 plus z equals 8. So we have 3 plus 8, which is 11, plus z equals 8. So z equals 8 minus 11, or z equals negative 3. So when you write your solution set, be sure that you use parentheses because you want to indicate that there is only one solution. Always x first, then y, then z. And then we are pretty much finished with that. Now, the reason you want to use parentheses is because if you don't, the system is going to recognize that a system such as my MATLAB has three distinct solutions, which is not what you're trying to indicate. You want to show one solution which happens to be an ordered triple. And make sure you absorb that. Again, a good idea is to pause the video. If you didn't get the correct answer on your own already, try to see if you can just put a blank piece of paper, work the problem out, and make sure you can get that before you proceed. While I erase the board. Okay, here's the third example we're going to look at. And in this case, you can either go with X, you can go with Y, with Z. They're all pretty nice to work with. So go ahead and pause the video and pick one of those variables to eliminate. It may or may not be the one that I'll choose in a second, but you should definitely try to solve it on your own before you continue. Let's make this as similar to a class situation as possible for maximum benefit. Okay, so welcome back. Now, while all three are pretty nice to work with, it looks like Y and Z would be a little bit easier to work with because there's a sign change here. So only for that reason, I'll go ahead and eliminate Y this time, so Y doesn't feel left out. Okay, so let's go ahead and try to eliminate Y from let's call this equation 1, 2, and 3 again. So we'll try to eliminate Y from 1 and 2. And for that, we're going to have to multiply the first equation by -2. So we get -2y and 2y, and they'll get eliminated. So we're going to multiply the first equation by -2. So we get -4x minus 2y minus 4z equals -2. If you notice that you tend to make mistakes with that operation, do this. Just put a -2 above each of those terms, like that, so that you don't leave any term behind while you're doing the multiplication. If you are comfortable enough, you don't have to do that. But just as a suggestion, if you used to usually missing one of these multiplications, then you can always do that. So remember, for equation 2, we're just going to bring it over as is without change. So we get x plus 2y plus z equals 2. Now we're going to add the two equations, and we're going to get -3x, the y's of course cancel out, minus 3z equals 0. And yes, that can happen too. Just don't leave these here blank, because I know sometimes when it's 0, you don't think you need to write it. When 0 is the only thing that there is, you need to write it. Otherwise, it won't be an equation. An equation has to have an expression on each side of the equal sign. So you must write the 0. Now we're going to go ahead and eliminate y again. Remember, we have to eliminate the same variable twice. But this time we'll go with equations 2 and 3. So, and it looks like to eliminate y from those two equations, all I have to do is multiply this third equation by 2, and that should be easy enough. So I'll bring the second equation over as is. I get x plus 2y plus z equals 2. And the third equation we're going to multiply by 2. So again, if you think you'll forget some of them, just write a 2 below each term and multiply. So you end up with (2x minus 2y minus 2z equals 0. We're going to go ahead and add the two equations, and we end up with 3x, these cancel out, minus z equals 2. So let's call this first equation, new equation that we obtained, number 4, and this one number 5. So we're going to bring number 4 and number 5 here and make a new system of two linear equations in two unknowns. So we have negative 3x minus 3z equals 0 and 3x minus z equals 2. Don't forget where we're headed. We're trying to find that point of intersection. So you can see how doing it graphically would not be the easiest thing in the world. Again, we got lucky. We got one of these systems where we're ready to eliminate one of the variables. So we can go ahead and add these two equations, and we'll get negative 4z equals 2. I intentionally picked this one because I wanted you not to panic when you see a fractional solution. And that's what happens here. When we divide both sides by negative 4, we actually end up with z equals negative 1/2 after simplifying the negative 2 over 4. So no problem. We're just going to take that, plug it into one of these two equations, and get the value of x. I'll just go with the second equation, number 5. So we have 3x minus negative 1/2, or 1/2, I mean, equals 2. So if I just multiply those negatives, I end up with 3x plus 1/2 equals 2. Of course, fractions are only scary if you don't know how to deal with them, but we've learned how to deal with them quite efficiently. So we'll go ahead and actually clear the fraction by multiplying both sides by 2. So we get 2 times each of the terms because of the distribution, and we end up with 6x plus 1 equals 4. So let me continue up here. So I get 6x equals 4 minus 1, 6x equals 3. We're going to divide both sides by 6, and we're going to end up with x equals 1/2 after we do the reduction here, like that. All right, so now we have x, we have z, and we're going to get y from one of these three equations. Let's go ahead and go with that last equation. It looks pretty simple. So we use x equals 1/2 and z equals negative 1/2 in, let me just write it down instead of saying in equation 3, in x minus y minus z equals 0 to get what's left, which is y. So we're going to end up with 1/2 instead of x minus y minus negative 1/2 instead of z, and that should all equal to 0. So I get 1/2 minus y plus 1/2 equals 0. So 1/2 plus 1/2 gives me 1 right there. Those two give me 2/2, which is 1 minus y equals 0. Sorry. And now we'll go ahead and move the negative y to the other side to become y, and we keep the 1 on the left side, and there's your y. And I've already verified this, so but if you don't have the verification, you can always do a quick check, especially when you get fractional answers like this. At the very least, just get a calculator and do a quick check that way. So we end up with ordered pair 1/2, always x first, then y, which is 1, and then finally z, which is -1/2. Make sure that you use parentheses to contain your ordered triple. I believe I said ordered pair, I meant ordered triple. All right, so make sure that you are comfortable with this one, with the fractions. Again, your best bet is to pause. If you didn't get this solution, go do it on your own and come back. But before you do that, I want to quickly show you how you could check on a calculator at least. So here's a calculator. We can take the first equation and substitute these values in it, see if it agrees. So we're going to take 2 multiplied by 1/2, which is x, and we're going to go ahead and close that parenthesis, plus y, which is 1, and then plus 2 times -1/2. Now, as soon as we hit the equal sign, what we hope to see is a 1, which we do, okay? So now you could either type that again, or you could actually copy that by just going over it and then hitting that, and then you can just go change those values. Actually, forget that. I thought we were going to plug into the same equation. Ignore what I just said. So we're going to go to the second equation, which is going to have 1/2 in it. So 1/2 plus 2y. So that's going to be 2 times 1. And then plus z, which is -1/2. When we hit enter, we hope to see 2, and we do. The last equation, we have x, which is 1/2, and those parentheses are actually optional. It's just a habit I have to go ahead and contain those in parentheses, but they are optional. -1 minus -1/2, which actually just becomes plus 1/2. This time we hope that when we hit enter we get 0, and we do. So that's how you can quickly check on a calculator to make sure that you have the right solution. And that is that for this problem. So go ahead and make sure all that is absorbed while I erase the board. Okay, so this is the last problem we're going to look at today. I just wanted to make sure that you can handle situations like this. These are considered systems with one missing variable. They are still considered to be linear equations in 3 variables. It's just that, for example, in the first equation, the coefficient of z is 0. You have 2x plus y plus 0z equals 6. In the second equation, the coefficient of x is 0. So you have 0x plus 3y minus 2z equals -4. And in the last equation, the coefficient of y is 0. So you have 3x plus 0y minus 5z equals -7. So they are still considered such linear systems, and they still generate planes like this, and you can see the solution right there, the point of intersection. So approaching these is just slightly different, because what you end up doing is just going ahead and picking 2 of the equations and eliminating one of the variables. For example, if you take the first 2 equations and eliminate y, notice you'll end up with an equation in x and z. Well, as it turns out, you already have another equation in x and z. So then you can take that new equation, put it together with this, and you have yourself a system that you can solve. So that should have been enough of a hint for you to be able to do this on your own. So you know the drill. Pause the video, see if you can follow what I just said, and get the answer on your own before you continue. All right, so I hope you did what I recommended. And here we go. So we're going to take the first two equations and we're going to eliminate y. So that means we can multiply the first equation by -3. So let's do that. So let's multiply the first equation by -3. So we end up with -6x minus 3y equals -18. The second equation we're just going to bring over. So we get 3y plus, let me change that back. Okay, so I'm just going to put the 3y over here because I want them to line up. I'll put the -2z first. So I'm not changing the equation, I'm just changing the order of the terms. And you know you can do that as long as each term keeps its sign. And notice here, the 2z was negative, it's still negative. The 3y was positive, and it's still positive. Equals -4. Now when I combine them, they're nicely lined up. So we get -6x minus 2z equals -22. Make sure you don't combine those. Those are different terms. They're not like terms. This has an x in it, this has a z. So you just combine them like this. You just write them out. -6x minus 2z equals -22. Now we're going to take this equation and we're going to put it with that, and then you have a new system in two variables. But before I do, remember, never lose an opportunity to simplify life. As you have noticed lately, it's complicated as it is. So we notice here there's a common factor of -2 we can get rid of to make this equation much nicer and simpler looking. So we'll do that first. Let's go ahead and get rid of -2. That's called dividing -2 off, because it's literally going to come off the equation. So we get 3x plus z equals 11, a much nicer looking equation. So now we're going to take this third equation here and put it together with this other equation we just found. And why? For obvious reasons, because they're both equations in x and z, which we can easily solve. Now, in order to eliminate x, I could multiply one equation by -1, etc. But I don't have to. I can just subtract the equations. That's a nice trick to know about, because why waste time with an extra step and you don't need it? Just go ahead and subtract the equations. So just be careful. So 3x minus 3x gives us 0. They cancel out. -5z minus 1z gives us -6z. -7 minus 11 gives us -18. Divide both sides by -6 and we get z equals 3. Now we're going to take z equals 3 and we're going to substitute it in one of these two equations to get x. So let's just go with this. So we're going to take this and this. So we end up with 3x plus 3 equals 11. So we get 3x equals 8, or x equals 8/3. So now we have z and we have x. All we need is y. So I can actually take either x or z and go into one of these equations and get y. I'll just take z because it's a whole number, makes life easier, and I'll go into the second equation and get y. So I have 3y minus 2z equals -4. Notice I just brought this equation over, and now I'm going to plug in 3 for z. So I get 3y minus 2 times 3 equals -4. So I get 3y minus 6 equals -4. So 3y equals -4 plus 6. So I get 3y equals 2. Therefore, y equals 2/3. And now we have all three coordinates, so we're ready to write our ordered triple, which represents the solution. So we're going to have 8/3 for x, 2/3 for y, and 3 for z. And that basically is how you solve systems of three linear equations in three unknowns which happen to have one solution, which is the most common type that you will encounter in this class or other classes. And so until the next time that we meet, be safe.